we're going to take a look at pointers and how pointers work in Go, but the implementation will be different in other languages, but the concepts are the same. And so when you hear about, the first thing you need to know is that everything in a computer is stored somewhere, right? Everything is stored somewhere. And so computers run on electricity. You know that? Electricity can be on or off. And based upon whether or not something is on or off, we could store and convey a message. Think about your porch light on Halloween, which is coming up. If that light is on, it means one message, and if it's off, it means another message. Come trick or treat or go away, right? That's like super simple, basic first step of a computer. It's electricity that's either on or off, and it's storing and conveying a message, right? On, come trick or treat, off, go away. What if we had two porch lights? Well, now they could both be on, they could both be off. This one could be on, that one off, and this way, that way, right? So we could store and convey 4 messages. And we could create our own coding scheme. Hey, if they're both on, party's on at my house. If this one's on, that one's off, study night. That way, movie night. Both off, go away. I could give that coding scheme to all my friends, and based upon the state of those circuits, whether they're on or off, and the arrangement of their on or off, that is going to tell us, the coding scheme, it will tell us what, it'll convey information. 4 messages with 2 lights. 3 lights, we could store 8 messages. 4 lights, 16. 5, 32. 6, 64. 7, 128. 8, 256. It goes up 2 to the power of n. So the number of circuits that I have, 2 to the power n messages I could store. 1 light, 2 to the power 1, I could store trick or treat, go away. Right? 2 lights, 2 to the power 2, I could store 4. 3 lights, 2 to the power 3, I could store 8. That's why when you hear in computers numbers like 16, 32, 64, 128, 256, 512, 1024, those are computer numbers because it's 2 to the power of n. You're going back to circuits that are in an on-off state. And the n is how many circuits are being stored there. So we're storing information. And we have to figure out where we're going to store that. And that has to be stored somewhere. By the way, instead of saying on, off all the time, this blows people's minds sometimes, right? We say, 1 is on, 0 is off. That's what we say. Because it's like, I don't want to say on, off all the time. 1's on, 0's off. And that's, power in an on state or an off state. Well, here's the power symbol, which allows you to turn power into an on state or an off state, and it's made up of a 1, which means on, or a 0, which means off. Like most people, they never realize like that connection. How many people knew that already? How many people just kind of like had your mind blown? You're like, oh, that's trippy, that's totally cool. That's binary right there. It's 0 and 1. 1 is on, 0 is off. And that goes back to the fact that computers run on electricity. And if it's in an on state or an off state, we can store and convey something. And so when we store information, we could store it way out in secondary storage, which is permanent, like hard disk drive, solid state drive, CD, DVD. Power goes out, it stays there. Or we could store it in RAM. And when we store stuff in RAM, which is primary memory or memory, primary storage or memory, when we store in RAM, RAM is random access memory. Random access. It's not sequential access. Your cassette tape in your dad's old truck is sequential access. If you want to listen to song 10, you got to go past song 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sequentially. In sequence. RAM is random access. You could randomly access any point in memory at any time. You don't have to pass anything else. Like, it's a CD. You want to listen to song 10, go straight to song 10. The laser just goes straight to that point and you start playing it. In memory, you randomly just access any memory. Memory will store values of a certain type. It's like cubby holes, and they each have an address. And things get put into those addresses, and it's stored in that address. So I could either, let's say I'm storing a chocolate milkshake up there. And Steve's like, dude, you got my chocolate milkshake? I could either go to that memory location, get the chocolate milkshake, carry that value over to Steve and give it to him. I carried the value over there to him. Or I could just say, Steve, it's in memory, it's in cubbyhole 14A. And Steve's like, oh, sweet. And then Steve knows where it's at. I could give him the address of where it's stored. I could either get the value and give him the value, or I could give him the address and he's going to be able to get to it when he needs it. I could either give him the chocolate milkshake, or I could give him the address where it's stored. And in either case, he knows where it's at. It's either in his hand because I gave it to him, or he's got the address so he can go get it when he needs it. So when I give him the milkshake, I gave him the value. When I give him the address, I'm pointing to where it's stored. I'm saying it's stored over there in 14A. I'm pointing to it. So that's a pointer. I gave him the address where it's stored. So in Go, let's create x colon equal 42, func.println x, right? There's the value. And then I could also do, boom, there's the address. So if I run this, what am I in? It's 5. I've got the value 42, printed that out, and then here's the address where it's stored. Let's print out the type. Let's assign to y colon equals. Let's assign to y this. And then let's print out what are the types of x and y. So the type of x is an int. The type of y is a pointer to an int, right? Because here, x is an int. When I take the address of where an int is stored and assign that with the short declaration operator, the short declaration says, oh, you didn't give me an int, you gave me a pointer to where an int is stored. I'm pointing toward that where that int is stored, right? And so here, the value, the type of y is that y stores a value of type pointer to an int. It's an address where an int is stored. So I could either give Steve the value, here's x, Steve, that's an int. Or I could give Steve the address where an int is stored, a pointer to an int. How many people that helped you? Nobody.
A little deeper, because I'm not sure why y is not just saying, oh, that's that address thing that you're pointing to, instead of being like, it's an int. It's not giving me that full, like, oh, I know what you're talking about. It's the address. It's just saying, oh, I know it's a pointer to an int, but I don't know what that address thing is. Like, it's not printing out the actual, you know, that long address that X did. It's not saying, oh, yeah, I know what that is. It's that. It's saying,
oh,
no,
it has the address too. So so the value is 42. I don't know what, oh, I need to do this. The value is 42. It is of type int. The value is this address. It is the type pointer to an int. I was just showing you the type. Here's the value. Here's the type. Here's the value. Here's the type. And these are two different types, right? This is an int. This is an address where an int is stored. Oh, well then it's a pointer to an int. I'm pointing to where an int is stored. So in Go, we always say pass by value. When you hear pass by value, pass by reference in other languages, I don't know what the hell they're talking about. We are always passing values in Go, right? Like I am passing either a 42, and that's a value, or I'm passing an address in memory, and that's a value. 42, what type is that value? Well, it's an int. This address, what type is that value? Well, it's a memory address where an int is stored, so we call it a pointer to an int. So this value is of that type.
So as a pointer, it's a type. Pointer is a type.
Yeah. Yeah, it's a pointer to something. Pointer to a string, pointer to an int. Yep, it's its own type. And then what you could do in Go, I don't know where you hit the wall with C++, but that's the main thing. And then just to explore a little further, if I wanted to, I could say y is equal to 40, I don't know, 100, right? And I could print line x, and I could print line y. And what I need to do here is actually do a little operator right there. And I'm saying, look, I know this is a memory address, this y, but I want to operate on the value there because I could get to that value. And the way I could get to that value is I could get to that value by, with y, I could put a star in front of it, and then that dereferences the address. So it allows me to access the value. So I'm just going to comment this out for a second. And so that last one, we're going to look at that point, that dereference. So right here, y is storing that. It's a pointer to an int. But if I put that little asterisk in front of it, right here, it gives me the value that's in that address. So if I then do this, say, hey, that value that's in that address, assign 100 to it, right? Now what will be stored in y will be 100. But check this out. What will be stored in x will be what? Somebody tell me the value on line 18. What's it going to print? What's that value going to be? Wrong, 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 wrong. Look at the code. X is 42. Print out the value of x, 42. Print out the address, some address. Give me the address where that x is stored, assign it to y. Sweet, y is storing that address. Here, print out the value and print out the type. This is 42, and that is type int. Print out the value, it's some memory address, and it's type pointer to an int. Dereference that, give me the value, you're going to print out 42. The value stored in this address, assign it to 100. Okay, what's the value at this address? Well, that's going to be 100. And what is x? X is a location where an int is stored. What int is now stored in that location, that cubbyhole at the mailbox? I took 42 out and I put 100 in to that memory address location. This is now going to be 100.
What do you mean by dereference?
This is a dereference right here. So this is, I'm referencing an address with y. It's a pointer. And here, dereference it. So just give me the value instead of the address.
So at which line does x change from 42 to 100?
Right there. Because this is all operating on the same memory address. Here's the memory address where the value of the int is stored. This is the same memory address pointing to the same location, right? I print out what's in that location, right, which is 42. And then I change what's in that one memory location. We got two variables pointing to the same memory location, right? working with the same memory location. And so now let's just see it run. 100, x is 100. We could do this, make it a little bit more clear. Isn't that cool? What's up, Steve?
Is there ever a situation where you would want to programmatic, like actually print out the address of something? Or
Sure.
is it just an idea that no one really uses? You'd never really want to print out the address of an int or whatever.
Yeah, I think I've never had that situation, but you know, you have to know, hey, am I giving you your milkshake, or am I telling you where your milkshake's stored? You know, so, and then when I tell you, there's some address.
Okay.
But mostly it's just like, you know, do I want to, let's say it's not milkshake, but let's say it's my car. Do I want to go get my car and drive it onto campus and deal with the police and come over the grass and then try to go up to the second story of the building with my car and be like, Steve, here's my car? That's a lot of data to move.
Yeah.
I think I'm just going to leave that data out in the parking lot and say, Steve, my car is at location 42 in lot D. And you'll be like, sweet, I'll get to it. Right? So I could just share an address and it's like less stuff to pass around. So maybe I have some huge billions of records stored and I don't want to pass all that through my program. I just pass the memory address.
Like, quick scenario, like, where is the most efficient way to use the pointer?
Yeah, when to use pointers? That's a really good question. So if I need to change something as it's moving through my program, having the address will allow me then to change it. So for mutation would be a word that you'd hear sometimes in books, right? Like as I pass something into different functions. So to illustrate that, or if it's just like a big thing that I don't know. I like sequence. And fump.println, right? A is going to be 42, and then we're going to call foo, and we're going to pass in a, and then we're going to say, you know, B here is equal to 43, and fump.println B, right? And then after we do that, we'll print out the value of A again. And then we'll do all this again with bar and A after bar. And we're going to pass in here the address because bar is wanting a pointer to an int. So we pass in an address where an int is stored. And then we're going to say, okay, C is an address, but I'm going to dereference it, and I'm going to make the value there 44. And I'm going to fump.println C. And C, I want to dereference it, so I want to see the value. Oh, we could do it both ways. Right? So we'll see C is an address, and we'll see C dereferenced as a value. And then we're going to come after we've ran bar and done that, we passed in the address, and then here we change the address, right? And so A will now be the changed, whereas B, when we change B, B's just like, you know, this is its own scope, right? So B's a variable. We passed a value here and assigned it to B, and then we worked with B and printed it out and left, and then we came back up here. It never affected A. Like, that's the scope of B right there. That's different than A, right? C, however, since it has the same memory address, when we change what goes on here, man, we passed in the memory address of A, right? We could better know what we're doing, because when we did this right here, we just changed stuff way over there, right? So that's mutating. So that's one case for using a pointer. Mostly stay away from them until you like, you know, like get up into like higher levels of like, oh crap, okay, I need this to be able to be changed in a couple of different locations, and I need it to be able to mutate as it goes through my program, and so I'll pass in some pointers. So if we run this now, we're at 06.
So it can be hidden counter or something.
A hidden counter?
Yeah, like something in the background for me, because I'm getting to that address every time something happens in the program. Add number in here in the address.
Yeah, in different locations. But then you got to be careful of race conditions, and so then you want to start looking at concurrency. Like if two different parts are like accessing a value and changing it, but at different times. Like here's two different areas of my program running in parallel, and you know this one gets A42, this one gets A42, this one adds 1 to it and writes it back 43. This one adds 1 to it. It was 42 over here. Writes it back as 43. We had 2 increments, but now it's only gone up 1. That's a race condition. So A is 42, B is 43. A after foo ran is still 42. C is that. C star is 44. A after bar ran is 44. Do we make it 44? Yeah. Okay, 42, 43, 44. Sweet, right? You all should, when Brian comes back, say, look, man, we talked with Todd, and we think that maybe we should, like, learn Go instead of C++. Just say that to him and just watch his face go like, what?
The whole class is converted.
And then you can say, dude, it's your fault. You were sick. You shouldn't have had him come sub. Pizza Hut, dude. He's got a student working at Pizza Hut. So that's it.
Quick question.
What's up?
You can only change something with the ampersand in front. Like that's the thing that's going to change if you put the point on. Is the